Okay, so in this video, I'm basically going to just jump into vectors from like a know-nothing standpoint to a point where you're pretty much functional enough with vectors to go ahead and do, like college level fucking math and physics. So let's start off by introducing vectors. So you might have heard of them before in a math or physics class, and if not, maybe you've seen Despicable Me, so you've heard of the dude Vector. This guy over here. So in Despicable Me, he's called Vector because he has magnitude and direction, or something. I haven't really seen Despicable Me, but he says something along those lines. And that makes sense because magnitude and direction are the two distinguishing qualities that vectors have that makes them vectors in their own little separate thing. So magnitude and direction. Generally speaking, nobody walks around talking about things like magnitude and direction, so it's a fair question to ask, what is magnitude, and what are people talking about when they say direction? So, magnitude, lots of things have a magnitude. Magnitude, by definition of the word magnitude, is just a size or measurement. In fact, there's lots of words that you can use in place of magnitude. So examples of magnitudes are your height, speed, your mass, the price of something, and things that only have magnitude are called scalars. This is because these are items that only have a scale, like a measurement. When you use a scale to measure things, this is why they're called scalars. Direction, though, is a little bit different, and it pairs with magnitude. So I mentioned earlier that speed is a scalar, but that doesn't really tell you a whole lot. If somebody's going 70 miles per hour, then you'd better hope that they're not heading in your direction, because if they hit you, then you're gonzo. Similarly, if you and your friend need to be somewhere and you're both running late and you're in the car with your friend and your friend's driving and all you know is that they're going 70 miles per hour, well, you'd kind of want to know if they're going 70 miles per hour in the right direction or if they're going in the wrong direction, right? Sometimes more information is needed. And so this need for more information distinguishes a vector from a scalar. Vectors give you information about the direction of a magnitude, which in the case of when you're running late is important sometimes. So vectors aren't this like obscure thing. They're everywhere all the time. You probably already know some without knowing that you know them. So common vectors are velocity, right? You may or may not have heard of velocity, but it's a vector. It's speed. It's the speed of something with a direction. So 70 miles per hour east is a velocity. 70 miles per hour is just a scalar, right? That's just speed. Same way, 70 miles per hour north is a vector. So acceleration is also a vector. This acceleration is the rate of change of velocity. So, the rate at which something's speed is changing. So if you're speeding up, then you're accelerating. If you're slowing down, then you're accelerating. But you're accelerating in a direction. You're speeding up in a direction. Nobody is just going 70 miles per hour. Somebody's going 70 miles per hour east, west, north, south, like that. And so again, if you didn't include the direction of this information, you wouldn't describe it as acceleration. Just saying they're increasing by 1 mile per hour every 10 seconds isn't acceleration. That's just the rate that they're changing their speed. Force is also a vector. So when you push something, there's an amount of strength that's in that push, and this strength is the magnitude of that force. So when you push something, it gets pushed in a particular direction, and this is why force is a vector, because it has a strength to it, a measurement of how powerful it was, the magnitude of the force, and also has a direction, because when you push something, it gets pushed in a particular direction, or you're directing that push, that force, in a particular direction. So here are some less common vectors. Weight is a vector. weight is the product of something's mass and the downward force, the downward acceleration due to gravity, which is noted as little g. And so the equation for weight generally is weight equals mass times gravity. So this is actually why weight is a downward force, because it has the same equation as F equals ma, force equals mass times acceleration. Because again, it's mass times gravity. Gravity, in this case, is a downward acceleration. Yeah, so weight is just how much downwards force you exert on surfaces on account of your mass and Earth's downward gravitational pull. And this is why your weight is actually less on the moon, because there's less gravitational pull downwards. So there's a smaller value for g. And, so like in the same way, 5 times 1 million is a big number. 5 times 1, 0.0001 is a small number. Same idea. But quick note, since vectors have a direction, they always have to be at least two-dimensional. There's no such thing as a one-dimensional vector. Doesn't make any sense. You can't have direction in one dimension. Well, you can, but just there's no such thing as a one-dimensional vector. So yeah, I mean, oftentimes we'll start off with like two-dimensional vectors and three-dimensional vectors. It's not going to really get, more than that. There could be, but there's not going to be. So there's a couple ways you can write vectors. So drawn out, a vector looks like this. Now you might say, oh, that's a line. Well, yeah, I mean, vectors and lines are very similar. In fact, don't quote me on this, but the way I like to think of it is that vectors basically are lines. Like the way you can treat them is very similar. I mean, there's not necessarily the same equations. Like you can't bust out y equals mx plus b for a vector. That doesn't make any sense. But I mean, in the same way you draw a vector like this or like this, and in the same way you would draw a line like this, I mean, you would include the head like that if it's going to increase forever. But yeah, they're similar. So a vector, let's say v for vector, is written like this. And you could also see that here in the little PDF. It's the variable it's assigned to it, v, with a little arrow over it. Now, that's it. If you notice, it took me a little bit of time to actually physically write that out. It's pretty much acceptable to do this, just the variable with like a little half arrow, the arrow cut in half without the other half with the little thing. That's okay when you're writing out, handwritten notes. But if you ever have it rendered on a computer, it's going to look like that. So there's a couple ways to write a vector. So if we have a vector v, you could write it like this. Or you could write it like this. Or you could write it like this. And you could also represent it graphically, as in drawn out, like we were doing earlier, like this. These are all the same thing. They all convey the same information, but they're just different in subtle ways. For example, in this one, you have the variable, for the axis, overtly explained to you, its component. So, this is in an x, y, z coordinate system. And this one here is in terms of unit vectors, which is a vector with a little hat over it, or, so like this is I hat, they would call this. Generally speaking, though, I hat is pretty much the same thing as x, in the x direction. Generally speaking, these are indistinguishable. They tell you the exact same thing, these three layouts. For example, this one, it would be implied that this is for the x component, this is for the y component, and this is for the z component. So this is called componentwise. This is called, I don't know if there's a name for this one. This is called component-wise, and then this is using unit vectors, which is also, this is also shown in the little PDF I have on the side. Angular brackets, component-wise, and with unit vectors, and then graphically, of course. So as I wrote, functionally these are the same with the exception of the graphical method, but you'll often find yourself using the graphical method and one of the first three methods in conjunction when trying to find the solution for problems that involve vectors. There's a little note about component-wise form. Remember that vectors are at least two-dimensional objects. So in that case, for 2D vectors, they have two components, one for each dimension. As this usually plays out, because we like to use x and y for coordinate spaces, then they have two components, an x component and a y component. And these are denoted as v with a subscript x and v with a subscript y. Notice how I kept that these are a vector because the x and y components of a vector that only has, again, x and y components if it's 2D, are also vectors. So a good way to demonstrate this is, let's go ahead and have an xy coordinate system. So this is x, this is y, in the positive direction. If we have a vector v and it's diagonal, this means that it's traveling in the x direction because, look at it, it starts here and it ends here, so its x position has changed. So it has an x component, it's moved in the x, and it also has a y component because look, it starts here in the y, in the vertical space, and it ends here in the y. So it has some distance y from where it starts and from where it ends. And so what you can do then is, this means that there is another vector, v sub x, that points just like this. And look how it starts where vector v starts in terms of the horizontal space x. And it also ends in the same place. Similarly, it has a y component. And the y component starts where, vector v starts in terms of the vertical space. And it also ends where vector v ends in terms of the vertical space. So a vector like this has two components, which can also be written as two separate vectors. And when you combine vx and vy, the result is this vector here, just a vector v, plane. So this is where trigonometry starts to get involved. Between here, you have an angle. This is obviously a 90-degree angle right here. And vector v here forms the hypotenuse. So earlier I was talking about magnitudes. The magnitude of a vector is represented as absolute value bars around the vector, like this. This is how you represent the magnitude of a vector. And the way you find the magnitude of a vector is like this. So magnitude of a vector v equals the square root of its x component squared plus its y component squared. Well, this looks similar to something. What is that? It looks similar to c equals the square root of a squared plus b squared. From a squared plus b squared equals c squared, the Pythagorean theorem, you therefore have that if you take the square root of both sides so that you have just c, then you find that c equals a squared plus b squared. Likewise, I have a triangle here for this vector that I was representing. So the magnitude of a vector is given by this equation. It is the square root of the sum of all of its components, the sum of all of its components squared. So if I were to tell you that that the magnitude of vector v is 5, then we know that either its x component has to be 4, or has to be 3, and its y component has to be 4, or the other way around. And this is because if the magnitude of a vector is given by this, and I know the magnitude, then I have 5 equals the square root of, some number squared plus another number squared. So if I want to go ahead and get rid of this square root, then I'm going to square both sides. So then I have 25 equals some number squared plus another number squared. Okay, well, this is obvious. 25, using numbers that come from perfect squares, perfect squares are 1, 4, 9, 16, 25, 36, and so on. The only ones that would give me 25 are 9 and 16. So this is 9, or the square root of 9, plus the square root of 16, equals 3 plus 4, or I did it wrong, but you see what I'm getting at. You would use the Pythagorean theorem to solve for the components of a vector using the information that a magnitude of a vector is given by this equation, which directly mirrors Pythagorean's theorem. And this is why you typically use the componentwise form and a graphical method to represent vectors. Because, if not, how would you really have done this? You wouldn't have. People always do it like this. Okay, so adding vectors. To add two vectors, all you have to do is write them in their component form and add the components. So if you have a vector A equals 1, 2, 3, and you have a vector B, which is equal to 2, 3, 4, this can also be written as vector A equals 1x plus 2x, 2y, plus 3z equals, for vector B, 2x plus 3y plus 4z. These are all equivalent ways of representing the vector, but if you wanted to go ahead and add them, vector A plus vector B equals 1, 2, 3, because this is equal to vector A, plus 2, 3, 4. And this is equal to 1 plus 2, because we're adding the x components, 2 plus 3 for the y components, and 3 plus 4 for the z components. And I use little, simple numbers for this one to just make it kind of clear to follow. The resultant vector is 3, 5, 7. So if you wanted to subtract the vector, it's literally the same thing. If I had vector A minus vector B, and vector A is 10, 4, 3, and vector B is 5, 1, 8, then A minus B equals 10 minus 5 for the x component, 4 minus 1 for the y, and 3 minus 8 for the z. And again, I just got this from this minus this minus this, and this minus this. And this gives me 5 for the x, 3 for the y, and negative 5 for the z. If you wanted to multiply vectors, there's 3 different types of vector multiplication. There's scalar multiplication, and all this does is it just scales a vector, or in other words, it changes its magnitude. Scalar multiplication does not change the direction of a vector unless it's being multiplied by a negative scalar. And if you want to perform scalar multiplication of a vector, then you just distribute the scalar across all the components of the vector. So example 1 is if you have a times vector v, and vector v is equal to vx plus vy plus vz, just a component-wise expression of a vector, then the result is given by a vx plus a vy plus a vz, because all I did was distribute this a to its components. So another way of writing a v, knowing that v is equal to vx, vy, vz, is to write it as a times vx, vy, vz, and then I just distribute this a across all the components. I just like in middle school math, or I guess even high school math too. You just FOIL it. You just distribute it. Another example is 5 times vector v. If vector v is equal to 3, 4, 5. So again, 5v then equals 5 times 3, 4, 5. And I'm going to distribute. So then I have 15, 20, 25. Again, 15, 20, 25. Another type of multiplication for vectors is the vector dot product. This involves two vectors. There's no such thing as vector dot product with a vector and something else that's not a vector. So the vector dot product, though, it gives you a scalar. It just gives you a number. You don't get another vector back. When we were doing scalar multiplication here, you got back a vector. This is a vector. But when you do the dot product of two vectors, like vector v times vector u, with a dot product, so, there's a dot here, you just get some number. You don't get another vector. You don't get vector a, you just get a. And a could be anything. I mean, a could be 16, 12, 42, whatever. But yeah, so you perform vector dot product by multiplying each corresponding vector component and adding all the products. For example, you'd multiply the x components of vector 1 with the x components of vector 2, and then you do this again for vector components y and z, and then you would add all the products together. So if I had vector a dotted into vector b, this equals ax bx plus ay by plus az bz. Why? Well, vector a equals ax plus ay plus az. Vector b equals bx plus by plus bz. Right? Okay. Well, if I just said you distribute, you multiply these and you just add them together, you get something along the lines of, ax times bx. You put that off to the side. Multiply ay times by. Put it off to the side. Multiply az times bz. Put it off to the side. And so let's say that this equals let's say this equals j, this equals k, and this equals l. Then the result is j plus k plus l. Or in other words, ax, bx, by. J equals ax times bx. K equals ay times by. L equals az times bz. So here's an example now using numbers instead of it being more, conceptual. The dot product of vectors a and b, when a equals 3, 9, 0, and B equals 4, 5, 8. Okay, well, like I said, we just multiply the components together and then add it all up. So this then gives you, 3 times 4 is 12. 9 times 5 is 45. And 0 times 8 is 0. Zoom dot product. 3 times 4 is 12. 9 times 5 is 45. 8 times 0 is 0, which gives you 57. The dot product of these two vectors is 57. Final type of vector multiplication is the vector cross product. The cross product gives you a vector back. Unlike a scalar for the dot product, and similar to the scale multiplication where you get a vector back when you multiply a vector by just some scalar like 5. So if I have a vector A equals 4, 5, 0, and a vector B equals 3, 9, 2, then the cross product, this little cross here, of vectors A times B equals, pay attention here because this is a little bit weird. It's, again, like I said, it's kind of hard to explain in words. You're going to make a matrix. And my physics teacher taught me to do this. Write these little unit vectors here, I hat, j hat, and k hat, and above them write plus, minus, plus. And then so write your vector. So we have vector A is 4, 5, 0, so we're gonna write 4, 5, 0. And vector B is 3, 9, 2. And notice how, this column here is the x components. X component of A is 4, x component of B is 3. Well, look, they're in the same column together. Same thing for the y components here. Y component of A is 5, y component of B is 9. Oh, look, they're here together in the same column. The rows just separate vectors. So vector A is in row 1, vector B is in row 2. And then we're going to go ahead and start multiplying, kind of. So the way I like to do it is I put my finger over it, but you can't see it because how are you going to see that on the screen? Just cover up this, pretend it's not there, and then only look at this for I. So we're going to make another little matrix here. And again, since we're not paying attention to what's boxed out in the pink, we're only going to pay attention to what's boxed out in the green. And we're going to write that. So 5, 0, 9, 2. And we're going to go ahead and put a little vector, unit vector here, I. And we're going to do the same thing now. But since we want, since we're not going to pay attention to this one, we're going to pay attention to these two. So let's make our little thing. And again, I put this minus here because this one is going to be subtracted from the previous one. We have 4 and 3. So you got the 4 and the 3 from here. The green ones are the ones we're paying attention to. And I have 0 and 2. And we're ignoring the j hat column. So that's also what we're going to put here. And here we have plus. So we're going to go ahead and add this next matrix. And now we want to ignore the k column. So we're only going to pay attention to the I and the j column, which gives us 4, 5, 3, 9. 4, 5, 3, 9. As you can see, 4, 5, 3, 9. 4, 5, 3, 9. Cool. So now we're going to go ahead and cross multiply. We're going to cross multiply and we're going to subtract. So here now we have 5 times 2 minus 0 times 9. And we're going to then do this for the next one. We're going to cross multiply. So we have 4 times 2 and we have 3 times 0. So 4 times 2 minus 3 times 0. Again, 4 times 9 minus 3 times 5. 5 times 2 is 10. 0 times 9 is 0. 4 times 2 is 8. 3 times 0 is 0. 4 times 9 is 36. 3 times 5 is 15. And so this gives us 10i minus 8j plus 21k, which is a vector. That's it. That's the cross product of two vectors. So as far as like vector operations go, until you get further into stuff like vector projections, that's about all you do. So, but let's say you have a graph and you have the origin here and you have some other point. Let's say this is 5, 3. Let's call this point A. A vector pointing from the origin to A is denoted as OA. Why is it OA instead of AO? Because the way vectors work with this notation is the second character indicates the destination, where it ends, and the first character indicates the origin, or where it starts from. So, I mean, it doesn't have to be the literal origin 0, 0. It could be like 5, 20. But yeah, in this notation, it's like that. And vector OA is equal to the destination minus the point of origin. So because it arrives at point A, it's more like vector OA is equal to vector A minus O. Okay, I made a little mistake here. These are not, A is not a vector on its own. A is a point. So vector OA is actually just equal to 5, 3. Why? Well, I mean, the origin is 0, 0, and if you're taking the destination point and subtracting it, then it's just going to be the destination point, with the origin in mind. Same thing if I had another point here, B, and it was like 16, 2, then the vector OB is just the point, it's just like the point. It's just the point B. However, if I had something like vector AB, then this is equal to OB minus OA. Why? Well, B is the termination point, and as shown, the termination point B is the same thing as just the point B, OB. So likewise, it's OB here, and the subtracting from the origin point A, OA. So this would then be given by 16, 2 minus 5, 3, which is 11, negative 1 is this vector. Also, earlier I was writing vectors like this. You can also write a vector like this. This is called a column vector. And I mean, you can also write a vector like this. Now, this is kind of weird because this looks like a coordinate. It looks like a point in a three-dimensional space, which is why it's best practice to write them like this. But in certain math homeworks and textbooks, you might also find them written like this as a column vector or as, you know, a row vector. And with a little symbol T called the transpose operator. These are equal. I mean, they tell you the same thing to begin with. Just, you know, it's a little convention as far as I understand. But yeah, as far as vectors go, this is all you need to know to start working with vectors. This is the introductory explanation of vectors. To be pretty competent in vectors too, because this is enough information on vectors to, you know, take physics 1 and 2, and to take like linear algebra classes. So yeah, this wasn't planned out too insanely particularly, but yeah, if you have any questions, I'm gonna answer them. I'm not like, if you have any questions, feel free to comment them. I'm not gonna get mad or anything. That would just be really goofy. Yeah, I mean, type them out. I'm sure there's something I might have missed or not explained too great. But yeah, thanks for watching.